Limits then. So we're doing this limit, which involves a square root. If you try to plug into this limit, it's the limit as x goes to 4. And you probably will notice something that when you plug in x equals 4, there's something bad going on the bottom, which is you have x minus 4. As x goes to 4, you have 4 minus 4, which is 0. But there's something bad going on the top too, which is you have the square root of x minus 2. Square root of 4 is 2. 2 minus 2 is also 0. So what is going on in this limit? That is what we're trying to answer. Let's take a look at what you said. All right. OK. All over the place, right, with this vote. So what have I said so far is that the top of this limit, square root of x minus 2, the top on its own is going to 0. The bottom on its own is also going to 0. What does that mean? It could mean a number of things. It could mean any of these things. So let's do a revote. This is all very split. Feel free to talk to your neighbors. We'll revote. If it's 0 over 0, what do you know for sure? That's what you should put in here. And also, by the way, you should also do this algebra bit as well. So I'll open it up one more time, and we'll revote. OK, let me give you just 1 minute to think what happens. And feel free to talk to your neighbors. Probably somebody sitting near you knows what is going on here. What should you do when you have this kind of limit? Is this your phone? OK. OK, 10 seconds left. Put in what you think happens when you have this situation where you're plugging in and you're getting 0 on the top and the bottom. What does that mean when you get 0 on the top and the bottom? OK, let's take a look at what people answered this time. All right, so still a little bit split, but one category got bigger than all the other ones, and that is this thing in quotes, which is type 0 over 0. And that is the correct answer. That is the correct answer. Why is this thing in quotes, and why don't I just say it equals 0 over 0? Well, equals 0 over 0, this option, is wrong. 0 over 0 is not a number. That is not what I'm trying to say. I'm trying to tell you that this limit is a limit where we are going to have to do some work and simplify it. So noticing that it's type 0 over 0 is not the final answer. It's just like an idea you have on the way to the final answer. So it tells you, look, this limit is not one of those simple limits where we can just plug in and know what it is. We're going to have to do some hard work, some simplifying to figure out what's going on. That's what it means. So when you see this type 0 over 0, that's what we're talking about. And when it's a type 0 over 0, you cannot automatically know that it does not exist or that it's infinity or anything like that. 0 over 0 could be any of those things. It could be that it doesn't exist. It could be that it's infinity. It could be that it's 7. You don't know. Just because it's 0 over 0, you don't know. You have to do the hard work and figure it out. We saw 2 examples of this last class. So I'll remind you guys of the examples. Where are the examples? Not this one, not this one. Am I in the wrong class? No, OK, 10, this one. So we saw 2 examples last class. This was one of them. We had x divided by x. X divided by x, that was a 0 over 0. And it turned out the limit was 1. So after simplifying, we got a limit of 1. This was another one, exercise 190. X squared plus x minus 6 divided by x minus 2. That was a different 0 over 0. And it turned out after working really hard, we figured out that the limit was 5. So sometimes it's 5, sometimes it's 1. It can happen that it doesn't exist or is infinity. When you see 0 over 0, it just means be ready to do something. Be ready to simplify. And that's what's happening in this problem, which, by the way, is the next problem here. Exercise 191 on page 395, 94. That's what we're doing. So before we actually start doing algebra and getting in the weeds with the algebra, I want to make sure the big picture makes sense. This is a limit where you should recognize that it's 0 over 0, and that means you're going to have to do some simplifying. Any questions or comments about this idea? Okay. So let's jump into it. The hint is to rationalize. And this is what you did on the high school algebra quiz as well. There were some problems like this. I think this problem literally appeared verbatim on the high school algebra quiz. Rationalizing here means to multiply by square root of x plus 2 divided by square root of x plus 2. And what I did to get this is I took the minus 2 on the square root. It was square root of x minus 2, and I flipped it into a plus. So whenever I saw the square root, I flipped the minus sign into the plus on the other term. This is called rationalizing. Rationalizing. Okay. And when you rationalize, there is a nice identity you can use. The whole point of rationalizing, the whole point of doing this thing with the flip is to use the following identity. Identity means an equation that is nice. If you multiply square root of x minus 2 times square root of x plus 2, that is supposed to be something nice. This is something nice. What is the something nice? Let's see if you guys knew. That was also in Math1030. Down here. Can I hide it? Hide results? And then I can click on this. Okay, so what is square root of x minus 2 times square root of x plus 2? Your answer will depend on x. So if you typed in something with no x, then it's definitely wrong. 0, 1, 2, 4, 6. These are all wrong, 34. What has an x in it? This has an x in it. This has an x in it. Some of these other ones have x's in it. The correct answer is this most common answer, x minus 4. It is x minus 4. So 10 people got it. 10 people got it right. 10 people got it right. I will say this one is the right answer to a different question. So we're going to see there's another question going on. This is going to appear somewhere. But x minus 4 is the right answer. When you simplify square root of x minus 2 times square root of x plus 2, it is x minus 4. Why is it x minus 4? It's a difference of squares. So it's a minus b times a plus b is, let me do it like this. A minus b times a plus b is a squared minus b squared. In our case, b is 2, and a is the square root of x. So it's difference of squares. So this is all very nice because when you use this identity, you get an x minus 4 on the top. So now I have this. X minus 4 is on the top. And now there's an x minus 4 on the top from this whole rationalizing business. There's an x minus 4 on the bottom, and those can cancel out, right? Because, you could say because x minus 4 divided by x minus 4 equals 1. I guess as long as x is not equal to 4, which is fine here because we're doing the limit as x goes to 4. We never care what happens at 4 exactly, only approaching. So those cancel out, and now we have this limit. Now we have this limit, 1 over the square root of x plus 2. Okay, and that is a limit we can solve. But really, I think the hard part of this question was getting to here. So I know I don't have the final answer yet. I promise you it will appear soon. You should ask yourself, do you understand what's going on to get from where we started to here? This is the kind of thing you got to do to solve these 0 over 0 limits. Any questions or comments at this point? How did I go from the 0 over 0 limit to this not 0 over 0 limit that I have now? Okay, so I've done the work. It started out as 0 over 0. Now it's 1 divided by something. It's definitely not a 0 over 0. Now I can apply the ordinary limit laws. So by the ordinary limit laws, so let's say by the divided plus and square root limit law, right? Because this limit is doing a 1 divided by something. That's the divided limit law. It's a square root, and there's a plus 2. So by those limit laws, I can move the order of the limit with those things. So I can replace it with this, the limit as x goes to 4 of x plus 2, like that. I can change the order of the limit and all these operations. Okay. And now I can do the limit. What's the limit as x goes to 4 of x? This is something you can definitely do. The limit as x goes to 4 of x is equal to 4. 1 over the square root of 4 plus 2. 1 over 2 plus 2, which is a quarter. So that's the final answer is a quarter. And it really, I think, is separated into two halves, right? There was the first half, which was getting from a 0 over 0, making the 0 over 0 disappear. That simplifying process, the rationalizing. And then there was the second half, which was solving that one. And that is like one we've done before, this solving one like that before. But this simplifying process, we haven't seen before. That was the new part. Any questions or comments about this one overall? OK, so this was the last example of doing an algebraic limit of the type 0 over 0. Like I mentioned a little bit last class, 0 over 0 limits are the most important thing with limits. The only reason basically to do limits is to do 0 over 0 limits. 0 over 0 limits are exactly what give derivatives. That's going to be in chapter 11, the next chapter we do starting next week. So this is a preview for chapter 11. In fact, if you already know what's going on, what we've actually done, we've done the derivative of the square root function. This is the derivative of square root of x at x equals 2. And we'll see that when we do chapter 11. If you've seen derivatives before, this should maybe connect with something. If not, you'll see it next week. Don't worry. OK, so we're going to move on to a slightly different topic, which is continuous functions in a second. Again, good time for questions or comments about these calculating limits. OK, and you have some homework calculating limits as well. OK, somebody doesn't want to calculate limits, so they left. OK, let's move on. Exercise 192, read on your own. This is like bonus. Like if you want to read it, go ahead, but not test it or anything. So yeah, I don't know. Up to you. Read it or not. We're going to move on to this stuff, which is continuous functions. Continuous functions. And if you remember from last class, continuous functions are to functions as squares are to rectangles. This was the analogy of the nice thing, right? When you have a nice object, it has extra properties, and you can use those properties to help you. The extra property we used last time was the just plug in property for continuous functions. But in this class, we're going to learn the intuitive graphical definition of a continuous function. So last time I said it was useful. You can do this just plug in. We're going to see that soon as well. But right now, we're learning the graphical intuitive definition. So a function is said to be continuous at a point if the graph of the function can be drawn without lifting your pen off the page. So when you're drawing a picture of the function, if you can draw it without taking your pen off the page, that is a nice property of a function to have, right? It means you can draw it in one stroke. It's kind of like all one thing. That is what continuous means intuitively. If it doesn't do this, if it's bad, then we say it's discontinuous. That's like a bad function, like you have to jump all over it with your pen. We're going to connect this to limits in a second, but before we do that, let's give you some examples, and you guys can tell me which ones are continuous or discontinuous. So we're going to do these examples, which are also in the notes. They're coming up in the notes. But first, take a stab at them and tell me, of A, B, C, and D, which ones are continuous. You can choose all that apply, so select all that apply. And I'll leave that open for you for, let's say, 1 minute. Let's try to do this one a bit quicker, because it's just graphically, you look at it, you decide, can you draw it or not? Only 0 time left. Put in your vote if you haven't yet. Which ones are continuous, which ones are not? Let's take a look. So, what did people say? All right. So overwhelmingly, everybody agrees D is continuous. D is continuous. Everybody says it is. And in fact, that one is sort of the easiest one. Can you draw D without taking your pen off the page? Look, here, I'm going to do it. Whoop, and then whoop. So it's no problem. You kind of do this. You have to pause at that little point to change direction, but that's okay. So D is definitely continuous. You guys all got this one right. Let's look at the other ones people chose. So C, most people think is not continuous. That is also correct. C is not continuous. If you're drawing C, you kind of come down this side of the line and you get stuck here at the point 2, 2, and there's no way for you to jump to the other half of the function, without smudging the page in a way that you're not supposed to. So C is also not continuous. B, you guys also got right. B is not continuous either for the same reason. It sort of has two pieces, right? It has this piece down here and this piece up here, and there's no way to draw it all at once. So B is also not continuous. A little more controversial is A. So 28 people said A was continuous. I guess that means like 50 people said A is not continuous, and the majority was correct as well here. So A is not continuous. Why is A not continuous? This time the problem is to do with this dot down here. So when you're drawing the graph A, you have two choices. You can either start on the curvy part, and if you start on the curvy part, there's no way for you to ever get that point. And if you start at the point, there's no way for you to ever get to the curvy part. So you're kind of stuck either way. You cannot draw A without taking your pen off the page. So that's the intuitive definition of continuous. And all of these issues, all the issues I just described, you can't draw it because blank, those translate into facts about limits. So we can recognize whether or not you can draw it smoothly by using a limit. And that's what we're going to do now. So we're going to fill in this part of the notes, which is I think 2 or 3 pages from here. Exercise 193 has options A and B. And instead of explaining in words, oh, you can draw it or you can't draw it, we're going to explain it using limits. So this one we said was not continuous because of this problem. We said this is some kind of issue, right? This point is an issue. And more specifically, you can see it's an issue by looking at the limits. So let's do the limit of the function. The limit of the function, well, there's two sides you can approach from. There's the limit from the right. This is the limit x goes to 1 plus, the right limit. The x values get really close to 1. What do the y values do? They go down to y equals 3. So the limit from the right is 3. The limit from the left, that's the left limit, x goes to 1 minus, that is also 3. That is also 3. The left limit is also 3. Limit from the right is 3. Limit from the left is 3. What is the limit, the two-sided limit? If the left limit equals the right limit, whatever that is the limit. So the limit is 3. So this function has a perfectly well-defined limit. A lot of people have a misconception that the limit does not exist because it has a hole. That's fine. It does have a limit. The limit is 3. Next up is what is the value f of 1. What is f of 1? And f of 1 refers to the value at the point x equals 1. That is this point down here, f of 1 equals 1. And this is the reason that this function has a problem. The value of the function and the value of the limit are two different things. They are not equal. Nicely behaved functions, the value of the limit is the value of the function. Like polynomials, you can just plug in. This is a function where you cannot just plug in. So you cannot just plug in. And if you cannot just plug in, that is what we mean by a discontinuous function. So this idea of not being able to draw it goes with the idea of limits that we saw last time. So the limit exists, but is not equal to the function. Okay. We've done limits before, so I did the limits quite quickly. This is a good time to slow down. If you have questions, please let me know. Okay, let's do part B. Part B, we also said there is a different issue going on here at x equals 2. There's another issue. And this time the issue manifests itself in a slightly different way. We can do the limits again. So we can do the right limit, x going to 2 plus, and we can do the left limit, x going to 2 minus, and they are two completely different things. So before, the right and the left side were converging together at y equals 3. Both limits were 3. In this situation, not only are they different, but they both explode in different directions. One of them is going up, up, up forever. The other one is going down, down, down forever. The left limit, the red stuff in red, this stuff, is going to minus infinity. And the right limit, the stuff in green, is going to plus infinity. So they're blowing up in different directions. We have infinity and minus infinity. What is the limit, the two-sided limit? It just does not exist. If the left and right limit are different, it doesn't exist. Okay, so there you go. We've already discovered a major problem with this function. The limit does not exist. That already means the function cannot be drawn in one pen stroke. To add insult to injury, not only can the function not be drawn there, it's not even defined, not defined at x equals 2. So at x equals 2, the function is not defined, the limit doesn't exist, everything is like a horrible mess. This function has a real serious problem. At x equals 2, it's not continuous there. Okay. Any questions or comments about this? We have 2 more examples to work through over here. Before we do the 2 more examples, let's go to the formal definition, which I hinted at last class, right? So the formal definition says the function is continuous. That is a shortcut. So continuous is a special math word that means the limit equals the value of the function. That's what it means. And of course, if continuous means that 2 things are equal, both things better be defined and they better be equal. So automatically, if it's continuous, you know it has to be defined, the limit has to exist, and the limits are equal. The limit equals the value of the function. So we already saw in these 2 examples 2 different ways you can be discontinuous. The one on the left, the limit existed, the function existed, but they were not equal. And then the one on the right, part B, nothing existed. Everything existed. Nothing existed at all. Everything was does not exist, does not exist. Okay. Questions or comments about A or B before we do C and D? All right, let's look at C and D. Here's options C and D. So again, this one is not continuous, and the reason is revealed by looking at the limits. So if you do the limit on the right limit, that is x goes to 2 plus, as this one, the limit is plus infinity, the y values shoot off forever. On the other side, the left limit, x goes to 2 minus, the limit is 2. The y values get closer to y equals 2. So that limit is 2. And because the left and the right limit are not equal, the limit just does not exist. As soon as the limit does not exist, we know the function is not continuous. So continuous automatically means that the limit would have to exist. Here's the situation, the limit doesn't even exist. So already not continuous. And so the value, f of 2, in this case is also 2, but it doesn't equal the value of the limit, not continuous. So not, maybe I can add a little note, not continuous, not continuous. Okay, what about this option, option D? Option D was the only one that was continuous, and you can reveal that it is continuous by looking at the limits. So in this case, you have the limit from the right, looks like this. That's x goes to 4 plus, we're looking at 4, and that's the right limit. And that is 2. And on the other side of the mountain, you're doing the left limit, and that's x goes to 2 minus, that limit is also 2. And the left and the right limit are equal, they're both equal to 2, so the 2-sided limit is 2. Last but not least, we gotta do the value f of 2. The value f of 2 is this purple value, and that is also 2, y equals 2. So everything is 2, 2, 2, 2, 2. The limit exists, it's 2, the value of the function is 2, they're equal, and therefore it is continuous at x equals 4. So kind of telling us that our intuition about drawing works in terms of just the limits being equal to the value of the function. Okay. Questions or comments about any of that? Now you guys know the picture, you know the definition. So in the notes, I think there's a couple more examples like this. These are more examples of the same exact thing, right? So here's 2 other functions. They have a left limit, they have a right limit. You can calculate, you do the exact same thing we did before. I'm gonna save these for extra videos, so I'll post these ones. These are more doing continuity, deciding whether or not the function is continuous by looking at the picture. And there's A, B, C, D for that. These are also extra videos. Because what do I want to move on to? I want to move on, I want to move on to this one. So in this problem, we already know what continuous or not means, but we don't have a picture. So this is a problem of deciding whether or not it's continuous using algebra. So is it continuous with algebra? With algebra. And I will give you a hint for this problem. We already did some of the limits for this problem last class. So if you flip back in your notes, you will find the limit of this exact function. And I want you guys to decide whether or not you think it's continuous and why in Math1030. Before I release you on Mathematize, I did also skip this one. This is another algebra example. This is an extra video, and I've already posted this one online. So we're gonna skip straight to this exciting piecewise function, because that's what I want to talk about. So I'll give you 2 minutes to do this one. Is it continuous or not, and why? There's a bunch of different reasons why. Okay, only a few seconds left. Put in your guess here for what you think is going on with this function. Okay, let's take a look at what people said. Is it continuous or not, and why? All right, so pretty split vote out of 77 people. 32 people think it is continuous, and I guess that means like 40 people think that it's not continuous for various different reasons. So let's look at the possible reasons it could not be continuous. I'm going to start with, I think, the easiest one. It's not continuous because the function is not defined at x equals 1. Remember, in piecewise functions, this is something we did earlier in the course, piecewise functions, I tell you different parts, different values of x, and I tell you what the function does on those different values. If I left out x equals 1, then the function would not be defined at x equals 1. But I think in this problem, there's a perfectly valid thing, which is if x equals 1, you're 5, right? So if x equals 1, the value of the function is 5. This thing is definitely wrong. The function is defined, and it's 5 at x equals 1. So that's not right. So maybe one of the other not continuouses are possible. I will also address this one. It's not continuous because it's a piecewise function. Whether or not it's a piecewise function, turns out, has nothing to do with whether or not it's continuous. So to evaluate whether it's continuous, you really have to calculate the limit, and you really have to see, is the limit equal to the value of the function? That's the only way to do it. There's no shortcut, like if it's piecewise, it's automatically continuous. If it's not piecewise, it is. Nothing like that works. They're two unrelated things. So that one's not right either. So it could be that the limit does not exist. It could be another reason. Let's start working on it a bit. I'll give you a chance to revote after we do a little more work. What I want to do first, before I let you revote, let's calculate the limit as x goes to 1 of f of x. Let's calculate what this is. Because really, checking if something is continuous is checking if two values are equal. One of the values is 5. The other one is this, the limit. We'll calculate them, and then we'll check if they're equal. If they're equal, it's continuous. That's what it means. If they're not equal, or this one doesn't exist or something, that's another way it can be not continuous. But let's do it. How are you going to calculate this limit? OK. There's like the real skill. I think the only reason math is like exciting and like people take it seriously is because math has this skill of you have a problem and you divide it into subproblems, and then you do the subproblems, and then you work your way up and you can solve some really crazy problems. Here's a simple example of that. We want to do the limit. How do you do the limit? Well, there's two subproblems. There's the limit from the left, and there's the limit from the right. You have to do both limits. So to do one problem, you have to solve the subproblems. Okay. And this is what we did last class. We did it exactly for this piecewise function. It was the exact same setup. I'll remind you how it goes. The limit from the left, x going to 1 minus. If x is going to 1 minus, that means x is a bit less than 1. And if x is even a tiny bit less than 1, then we automatically are talking about that branch of the function. So in the limit as x goes to 1 minus, the only values we ever see are values on this branch of the function. And so we can replace f with this thing, x squared minus 2x plus 4. Hopefully that should ring a bell from the previous class. By the same token, if x is going to 1 plus, x is going to 1 plus, then x is a little bit bigger than 1. And if x is a little bigger than 1, then we are in this one, that branch of the function. So that's the limit as x goes to 1 plus of 8x to the 4 minus x squared minus x minus 3. And that happens if x is bigger than 1. So again, this is a repeat of the ideas from before. I'm not doing them as slowly as I did before. Hopefully it's OK. You see what I'm doing. How are we going to solve these limits? Well, fortunately for us, these limits are both just plug-inable, just plug in, right? They're both polynomials, something with x squared, something with x4. We can just plug in. And when you plug in, you get the answers. This one is 1 squared minus 2 times 1 plus 4, plugging in x equals 1. 1 minus 2 plus 4 is 3. 3, OK. On the other one, it's also just plug-inable. It's a different formula, but we also plug in. 8 times 1 to the 4 minus 1 minus 1 minus 3. So 8 minus 1 minus 1 minus another 3. 6 minus 3 is also 3. 3. OK. So I did the left limit. I did the right limit. That was like the hard part. I did all of the subproblems. Now we just got to bring it back up. We got to figure out what is the limit, right? What is the limit? And then we have to answer the original question, is it continuous, right? So it's like layers on layers. We did the bottom layers. That was the hard work. And now we're like upper management, just like checking the boxes at the end. So I will let you revote. You can, from here, you should be able to figure everything out. I've done the sort of the hard work for you. Let's revote. So I'll do this one more time, and you can choose whichever one you want. I want this problem, OK. OK, start. OK, people are going quite fast. Let's do 1 minute. OK, there's like a few seconds left. Put in your guesses. All right, let's take a look at what people said. OK, so somewhat split again. So 40 people out of 75 are in is continuous. Half the people are in it is continuous. Half the people are in is not, but for various different ways. Some of them, I said, are just never going to be right. So it's continuous because it's a piecewise function is never right. That is not a reason something is or is not continuous. The reason always has to do with the value of the limit and the value of the function. So that's definitely wrong. I said that one already. It's not continuous because the limit does not exist. Okay, before I address this one, let's do this one. It's not continuous because the function is not defined at x equals 1. We said the value of the function is 5 at x equals 1. That's definitely wrong. It's not continuous because the limit does not exist. Let's look at this. We did the left limit, and we got 3. We did the right limit. We also got 3. That means the value of the limit is 3, right? If the left limit equals the right limit, the two-sided limit exists. It's equal to 3. So there we go. This limit exists. So that's not right either. If you said the limit, it's not continuous because the limit does not exist, that is also wrong. Okay, so what does that leave us with? That leaves us with it's continuous or it's not continuous for a different reason. I'm going to get you guys to revote one more time, and I'm looking for like a majority, like a solid, like we're all on board, we all know what's going on here. This is like the main concept of today. If you get this, then it shows you're understanding continuous functions. So we're going to revote one more time. The unprecedented third vote. Yeah. Okay. So think carefully. What is going on? What does it mean to be continuous? Is it continuous or not? And really do think about it. Like, don't. And again, feel free to talk to your neighbors. Okay, 10 seconds left. Make your final choice. Are you going to switch? Or are you going to stay in the same camp you were before? Okay, let's look. The third revote. Is there a clear majority? No, there's no clear majority. It's still super split. All right, this is what happens in the House of Parliament. Now we debate. I need one person from each group who will tell me why they voted for that. Someone who thinks it is continuous. Want to tell me why they think it is continuous? Majority group. Why is it continuous? If it is continuous, there's one thing that has to happen for it to be continuous. Yeah? Yeah? Yeah. Why? Well, how do you know it's an open dot at 3? Okay. So this is 5. So this, I think you're telling me that f of 1 equals 5, right? That's this line. And therefore it's continuous? So you're saying, I think I get what you're saying. You're saying we have this algebra, we have this 3 and this 5, and you are trying to translate into a picture for me. And I think the picture I'm understanding from your description is you're saying, here is y equals 3, looks like this. And we said the left limit and the right limit are 3. So the function, because of this thing, is looking like this. And then on this side, it looks like this. And then it has this hole right here. The limit is 3. But I know it's a hole because I know that f of 1 equals 5. So it looks like f of 1 is 5. That's at y equals 5. So you're painting this nice picture of a function that looks like that has a hole at 3, and has a filled-in thing at 5. And you're saying, therefore, it is continuous or it's not continuous? Therefore, it's not continuous. And very simply put, the reason it's not continuous is this value and this value are different. Okay. Very nice explanation of why it's not continuous. Would anyone like to tell me why it is continuous? So this is a nice thing that does not happen in real politics, is the side that is wrong usually is not silent and will give you some bad reasons. But I think you guys have figured out that this is perfectly correct. Very good job. This is exactly what's happening. That's what the picture looks like. It is not continuous. So very nice explanation here. If you selected not continuous for a different reason, you are correct. What is the different reason? The different reason is the limit exists and is not equal to the value of the function. So not continuous, and I'm going to say because limit is not equal value of function. Value of func. The limit was 3, and that is not equal to f of 1, which is 5. Okay. I promised I would finish class early. Please go vote on that thing. That's why we're finishing class early. Let me try to briefly Google it and find the link, which will be embarrassing, I guess. Arboretum referendum. So please, 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 go vote for this. I encourage you to vote yes, but of course it's up to you. But please do vote. That's why I gave you an extra 5 minutes of your life. Okay? Thanks very much.